It is our great pleasure to have Christoph Reisinger speaking at our seminar. And Christoph is a full professor of applied mathematics at University of Oxford, a member of several institutions, including Oxford Mann Institute for Quantitative Finance. He is also a fellow at St. Catherine's College, known for his work, starting back in the days on stochastic control and numerical analysis of associated PDEs that comes from the stochastic control, and of course on his contribution to stochastic modeling and computations, more recently on mathematical foundations of reinforcement learning and deep learning. And he's also currently editor-in-chief of the Journal of Computational Finance, but he also was the editor-in-chief of Applied Mathematical Finance, so definitely very well known in our community. Today's talk would be on risk management of option books with arbitrage-free Neural-SDE market models. And the rules are as always the same. The talk will last about 45 minutes. We'll have time for questions. Please feel free to type questions in the chat area, and we will either recognize you and you'll be able to ask the question, or I'll read the questions for those who post the questions. After the formal part, we'll stop the recording, and then we can talk with Christoph more informally in general about the talk, but also about the mathematics behind and applications. With that said, Christoph, one more time, thanks for joining us, and the floor is yours.
Oh, thanks very much, Igor, for the kind introduction and invitation. So this is a more recent venture of mine with my colleague Sam Cohen, and it's based on very strongly on an industrial project that was brought to us by the CME, the Chicago Mercantile Exchange, and that we worked on with a student, a PhD student of ours, Victor Wang, who's now in the industry. So the brief CME, who kindly sponsored this project, was to develop a model for the dynamics of large portfolios of financial derivatives, with the goal to be able to generate scenarios going into the future that they can use for risk simulations, for instance, to compute risk measures for these books of derivatives. So I'll be a bit more less ambitious in this talk, and I will focus on books of options on a single underlying, and I can allude at the end of how one may generalize this to more diverse option books. And the goal is that we may be interested in hedging other options based or exposed to the same underlying, but in particular I'll also show you investigations of risk management and estimation of things like value at risk. So to have something to talk to, I'm showing you here a bit of a cartoon of what I have in mind there. So I'm considering a single underlying, for example, an exchange rate like the euro-US dollar rate given on a certain day. And so here I have shown you dots that symbolize the range of strikes and expiries that are traded on a given day on these underlying. So we see that the spot at that point would have been something like around 1.15 or so, and each of these black dots, the coordinates correspond to a certain expiry and strike of a call option that were traded on that day. And we see that there's a number of traded maturities, so maybe in the range of 15, and then maybe on average about 20 or so strikes. And for shorter maturities, they're more concentrated to the money, and then they spread out over time and potentially have a drift as well. So just bear in mind that this is sort of not the classical picture of a rectangular lattice that is easier to treat with, but I mean, it's more of an unstructured grid of strikes and expiries. And what we're interested in is modeling the dynamics of the high-dimensional process that corresponds to the prices of these several hundred of contracts. So now, as you would imagine, given that we trade in contracts here with quite close strikes. So these will have a strong dependent structure, the dynamics for this book. And not only that there will be some statistical dependence. There will be some hard constraints that are dictated by underlying economic considerations. So in particular, the value of the derivatives will have certain relationships to the spot value of the underlying. And perhaps more importantly, there will also be constraints between these contracts. So for instance, call prices will be monotone decreasing in the strike, and there's a well-known further static arbitrage restrictions, for instance, convexity of options with a given maturity in the strike variable. And in this particular case, where we have this unstructured lattice, there's also fairly complex cross dependencies between triplets of pairs of strikes and maturities that give a certain cross convexity in both strike and maturity. And there's a comprehensive paper by Cousin from 2007, building on earlier work that derives precisely sufficient and necessary conditions on the relationship between all of these traded prices to give you a static absence of static arbitrage. And conveniently, that translates into the absence of model-free arbitrage. So it's nice that this one-to-one relationship between static arbitrage conditions and model-free arbitrage conditions. And given that there's a lot of these restrictions that would be in the hundreds or even thousands, in recent work with Victor and Sam, we managed to localize these and reduce the number of conditions to an equivalent set that is a lot smaller. So this is just to say that although we are formally modeling the dynamics of a process that has several hundred components corresponding to each of these traded contracts, we can expect them to live close to a much lower dimensional manifold that is constrained by restrictions. And I want to emphasize that given that we have all of these conditions are formulated as linear inequalities, what we're going to be looking at is an intersection of half spaces which are dictated by these inequalities. So for example, this monotonicity, convexity, they're all linear inequalities in these prices. And that means that if I look at this joint several hundred dimensional process, it will live in some high dimensional simplex that is probably quite squashed and narrows down the dynamics quite a lot. So one of the emphases of this work was, and that was something that was a desire from CME, that in simulating forward these trajectories, we do not introduce any arbitrage at any point in time, and therefore we have to respect these restrictions. So it's a well-trodden path to go from these arbitrage conditions to the existence of a pricing measure. So the steps that we would undertake is that we verify whether our inputs are indeed arbitrage-free, and so we have a simple check by a linear programming problem to do that. And then given that we have a discrete set, we may want to interpolate between them. And there's work by various people that you can do this in an arbitrage shape-preserving rate that maintains the monotonicity and convexity assumptions. And that results in a two-dimensional surface of maturities and strikes, satisfying certain conditions on the first derivative, the function, and second derivative. And that, of course, then leads via the Breeden-Litzenberger formula that leads to marginal laws for the underlying at all of these sets of maturities. And they will have the property that they're in convex order, considering the maturities, and that then leads to the existence of a Markovian martingale measure under which the prices have no static arbitrage, by work by Karl Madan and others. So the classical approach then to make this static object dynamic and simulate it forward would be a martingale approach that you model the prices of these derivatives as expectation under some pricing measure of the expected payoff given the observations up to that time. And that, of course, then automatically triggers arbitrage-free dynamics However, for our purposes, this is a bit cumbersome to do that, because first of all, we would have to calibrate the model. And if you want to calibrate to this rich surface of prices, we would have to use something like a state-of-the-art stochastic local volatility model, which requires quite heavy machinery involving either some particle methods in the spirit of Guillaume or Marie Labaudère, or some nonlinear McKean-Vlasov type PDs. And if you want to do this repeatedly going forward in time, that would be quite costly for the simulation. More fundamentally, perhaps, it is also well known that the calibration of these models changes over time. So the model that you calibrate today has to be recalibrated at future times, and making this dynamically inconsistent, which is, of course, unsatisfactory for risk simulation. And finally, in the context of simulating risks, we want to simulate things under the real-world measure, whereas the martingale approach would naturally sit in the risk-free measure. So you have to take additional steps to then simulate forward in the real-world measure. So our approach is therefore fundamentally different, in the sense that we are going to take the approach of a market model that doesn't start from the underlying and takes that as a primitive object, and then derives, using the martingale approach, the derivatives prices, but it starts by modeling the derivatives prices as the primitive objects already. So we're going to use so-called Neural-SDEs to do that. And before I explain what I mean by that, let me sort of survey a little bit of related background works. Of course, neural networks have been used very exhaustively in this context in the past few years, and for a review of all the works that are sort of pre-2020, I refer you to a very nice and comprehensive review paper by Roof and Wang, published in the Journal of Computational Finance a couple of years ago, where they go through the whole lot of papers that use neural networks for pricing and hedging, classified in the spirit of taxonomy, considering the input features, the learning process, etc. Now, more closely to our work are Neural-SDE models. So models where we write down a process as a solution of a stochastic differential equation, where the drift and diffusion coefficients are modeled by neural networks. So Christoph and her co-authors, they considered a local stochastic volatility model, where the local volatility component is given by a neural network, and then they train it using adversarial approach to calibrate that model to prices. Perhaps sort of more generically, even Lukas Spruch and his co-authors, they looked at even more over-parameterized model, writing down a Neural-SDE where both the drift and the volatility are given by neural networks, and then they used this over-parameterization as a way of assessing model risk. So as I already alluded to, our approach is different in the sense that we don't start by writing down an SDE model for the underlying, but we start by writing down a fully coupled SDE model for the option book, and in that sense, the model is more closely related to other market models that are quite common in fixed income markets. So, for example, the Histra-Morton or the BGM LIBOR market model, where you also have a set of strongly coupled, strongly correlated processes for forward type interest rates. And then you derive a drift condition, which gives you the existence of a martingale measure. Another strand of work comes from certain code book processes in the context, for instance, of equity derivatives. You may be interested in parameterizing prices, not in their sort of native coordinates, but by transformation, one of them being the local volatility. And then if you make that dynamic, you again get a set of restrictions for the drift, as in the work by Carmona and Natocci, for example. So it's in this spirit that we see our work. So I have to take a step back now and think about what are good coordinates to work in. So if I start with the plot here on the left, so what I'm showing you here is at a certain date, I'm looking at options with a certain certain fixed expiry and a certain moneyness. So we'll be starting with these options a year before expiry, so that will be starting at the top where we have a blue and an orange set of points that correspond to 2 strikes of 1.05 and 1.1. So then we move closer to the fixed maturity of 1 year, and because of the way that the spot moves, suddenly a far out of the option, out of the money option comes into existence, the green dot here, and exists for a while until it is not traded anymore because the spot moves away again. At the end, as you get to expiry, only one of these derivatives with strike 1.1 actually survives. So what this tells us is that it doesn't seem to be a good idea to model a lattice of options which have a fixed expiry, because they will come in and out of existence. At the same time, because of the way that options are usually traded around the money, it also makes sense to center them by looking at a moneyness and potentially a log moneyness. So because of these considerations, what we do is that we transform from strike and maturity scale into a log moneyness and time to maturity scale. And because of that, we can deal with the more static objects of liquid options that I'm showing you here on the right-hand side. So what we do is that we model a number of pillars, sort of a lattice of contracts that is thinned from the originally traded contracts. And we keep these moneynesses and time to maturities fixed, and we model the value of these derivatives as we go forward and interpolate in between if required. So we perform this transformation that I'm showing you at the bottom of the slide, where we rescale the surface by the forward and the discount factor as well. And that has the advantage that in the most basic of models, the Black-Scholes model, this object would be completely static, because we can write the rescaled Black-Scholes price in these coordinates simply as a function of tau and m of, and therefore this would simply be constant across time. Now, of course, we don't believe in Black-Scholes, and therefore we introduce additional stochastic factors. So what we do is, and this is really a key slide, so I want to sort of take time to explain this. So we're modeling options for a fixed range of time to maturities and moneynesses. So that's the object on the left-hand side as a time-dependent process. So to zeroth order, so this would be something which is static over time. So if I were to find the best constant approximation to this, you would simply be looking at an L2 projection. So we would be averaging snapshots of this surface over our time series. So this would be this factor G0 here. And under Black-Scholes, this is all there is to it. Of course, in more realistic models, you want to correct this for more stochasticity. And therefore, what we do is think first of if you want to capture the statistical properties of the surface, you might want to do a principal component analysis of your surface. So you have a potentially high-dimensional process that corresponds to all of these options, and you order the principal components in order of their variance, obviously, and you have a certain factor loading. So this GI gives you the exposure of a particular contract with a time to maturity tau and the moneyness m to a certain factor. So at that point, the way you construct the factors, you have certain freedoms that could be economic factors to best match the statistical properties to reduce the variance. You might want to do principal component analysis, but we will later also take arbitrage considerations into account to choose the factors in a way that the resulting approximation allows for as little arbitrage as possible. And for a set of Eurex index options, I'm showing you at the bottom here 3 plots for the first 3 factors. So the first factor is simply sort of a price surface where you have sort of this almost like a payoff behavior for short time to maturities, whereas for longer maturities, it is sort of more smoothed out. So you think of this as sort of the Black-Scholes price. The next factor turns out, although this is purely based on an automatic statistical reconstruction, turns out to be something like a volatility factor. So I'll come back to this. So we'll see that the exposure is largest close to the money and then increases over time. And then the third correction is sort of harder to interpret. So what I want you to take away from this is that we're reducing the surface further by a factor model, and we will find in practice that d equals to 2, so 2 exostochastic factors are parsimonious, a good compromise between being able to fit the data but not overfit. So what's important here is as well that this is a linear factor representation, and because remember when I told you that to be free of static arbitrage, the prices have to lie in a multidimensional simplex. Now, because I'm looking at a linear transformation to new factors, this corresponds to a simplex for these factors. So I'm showing you here sort of the cross section of these first 2 factors, Xi1 and Xi2, and the red dashed lines here are the boundaries of the arbitrage-free region. And therefore, the green shaded area here is the intersection of all these arbitrage-free regions. And we would hope that the market prices are all in this simplex. And indeed, it turns out that in this plot that they are. So what I'm showing you here is the transformation of the true market prices onto my factors, and then plotted as a scatter plot in this as coordinates here. Now, once we've done that in a static way, we sort of decoding this factor representation, we now want to make these factors dynamic and learn a dynamic model for these factors. And this is where the Neural-SDEs come in. So what we want to do is we want to learn a coupled model for the underlying and this factor vector Xi, where we parameterize the coefficients mu and sigma here by neural networks. And similarly, in our sort of exponential SD here, the coefficients for S themselves will also be parameterized by neural networks. In the future, to make our simulation easier, we will actually cook this down a bit further. And for example, in the Xi process, remove the S dependence and only learn a model for the factor itself, sort of assuming some sort of scale invariance property. In fact, we already made the assumption here that we have certain stationarity, and that is reasonable to make because of the transformations we made to our surface. But it is clearly a model that makes certain approximations. Okay, so 2 steps. Step 1, identify the important factors. Step 2, write down a dynamic model for those factors, which we can then learn from the historical time series of the derivative prices. So how about these arbitrage constraints? So I told you that we want to train the model in a way that we stay within this simplex. So there's some classical stochastic analysis that comes into this, which basically says that to stay within a certain set, the drift of stochastic process has to come inwards at the boundaries, and the diffusion is not allowed to cross the boundary. So on the left here, I'm showing you a condition here that the projection of the drift onto an inward pointing normal has to be positive. So as you approach the boundary, the drift has to come in. And the way we incorporate this is a little bit of a hack. So what we do is that we learn a drift vector mu hat, and then we sort of we push it away from the boundary. So if this was something that has a sort of a stray component that could take us across the boundary, we pull it towards a point that lies sort of in an opposite corner. So it's a simple way of sort of enforcing that the drift actually comes in. And we do this in a small layer close to the boundary. So we don't want to mess with our dynamics in the interior, but if we were to get close to the boundary, we sort of give it a push that it goes back inside. For the diffusion, what you need is that you're allowed to diffuse parallel to the boundary, but you're not allowed to have any non-zero volatility across the boundary. So therefore, the diffusion matrix has to degenerate so that the projection of the diffusion tensor in a direction orthogonal to the boundary is 0. And we do that by a coordinate transformation, where we simply project onto matrices where the component orthogonal to the boundary is equal to 0. So that gives us the following structure for a neural network. So we have a certain input layer, which contains the underlying and the factors. We then have a number of hidden layers with a certain width and a certain depth. That generates a certain first candidate for an output for the drift and the diffusion, which is then transformed in a way to ensure that we stay in the arbitrage-free region using the nonlinear transformations that I just outlined. Okay, so then you can perform a standard learning problem. So we perform some maximum likelihood estimation of a discretized process that just uses some standard Euler-Maruyama scheme. And then from the historical time series over a sufficiently long period, we learn the coefficients for our factor model. So the first thing I can show you is a synthetic market. So we tested the model first on an artificial market where a single trajectory was generated by a stochastic local volatility model. So you have a process for the underlying that contains a combination of a leverage function that depends on time on the underlying and the square root of a CR process. So we calibrate this model to the real market. Then we simulate the trajectory, and along this trajectory, we price options. And that gives us dynamics for a lattice of option prices that are consistent with this model. And then we forget about where the market prices came from, and we train our neural network model. And we see something interesting that, so on the left-hand side, what I'm showing you is a scatter plot of, on the horizontal axis, there's the true volatility. So going back in the slide, and apologies for the jumping. So I've defined this sigma US as this curly bracket here that contains the volatility of the asset process in my model. And then I have a learned neural network coefficients that approximates this, given our factor representation. And a sort of a straight line here would be optimal, that we've exactly learned the volatility and we're not too far from it. Perhaps even more interestingly, what we find is that the identified first factor Xi1 in the right-hand plot is almost identical to the stochastic volatility. So although we completely forgot about our model and we only used the statistical reconstruction for the best additional factor for the option surface, it turns out it is extremely close to the volatility. And in fact, it turns out that if we now were to learn the drift and the diffusion of this factor process, now working on the hypothesis that this is really a volatility, we see that we approximate the affine drift and the square root diffusion in a reasonable way. Of course, this is a statistical estimation, and we get a certain scattering around these functions that we would expect if it was truly the Heston model, but it's the right tendencies. So maybe let me then switch to true market prices. So we then applied this to Eurex options, index options, and the DAX. So I'm showing you here the EURO STOXX and the DAX. First the actual index, and then short-dated call options, just to have a visual. And then on the right-hand side here, again, a scatter plot of the different traded moneynesses and time to expiries. So we train a two-factor model, and to make it a bit richer, we also allow extra factors that are just simple OU processes. So I don't want to train a rich factor model where I have to train rich neural networks, but to have a little bit better fit to the market data, we allow so-called secondary factors, which just have a simple scalar dynamics. And it turns out that we can find a very good fit statistically where the mean percentage error of the prices in the range of 1%, and in only a very small fraction of the simulated prices is there some static arbitrage present, which we then eliminate by running a linear programming algorithm. Now here's something interesting. So So this is the top is sort of an in-sample scatter plot of the simulated factors. And what I want to illustrate by this is left that, well, first we are staying in the arbitrage-free region here. And also that the drifts here, they always sort of push us inside. So I'm illustrating this here by arrows, which give us the drift velocity, if you like. And we see that they're at most parallel to the boundary, but they never take us outside. And similarly, in the top right-hand plot, what I'm visualizing here is, again, for the simulated factors, the diffusion symbolized by an ellipse, where the two axes of the ellipse correspond to the principal axis of the diffusion tensor. And so what you see is that they get squashed to the boundary, illustrating the fact that the volatility component orthogonal to the boundary goes to zero. So we're learning the right type of dynamics which stays in the domain. And then I'm showing you also an out of sample data. So we've learned this model over the order of a decade in the past, and then we simulate forward over an extra year. And then we see that the forward simulation of the factors in the model, so that's the blue dots here, give you sort of a similar coverage as the orange dots are the simulated dots, and the blue dots are the ones that come from real data. So we see that in distribution, they look quite good. And a different visualization is on the right-hand side, where I'm showing you certain level curves of sort of a non-trivial joint distribution of these two factors, shown with the marginal distributions. And we can see that this has the right type of shape. And another way of looking at this is now showing you some implied volatility. So there's no sort of one-to-one correspondence between real data and simulation, because this is out of the money. So the point I want to make here is that there's a rich variety of implied volatility shapes. So shown in each of these boxes here is for the DAX, the smile for different maturities as a function of the moneyness, and so you can get all sorts of behaviors. And this is just to say that our simulated model allows a similar type of implied volatility structures. So that is reassuring that we get a similar behavior in the forward simulation. Okay, now what can we do with this model? So I want to show you two applications of our trained model. One is for hedging and the other is for risk simulation. So we're considering two types of hedges. The first one is sort of a standard sensitivity-based hedge, something that we teach in our courses in the Black-Scholes and Heston models. So what we do is, so we write down our factor model, and then we construct a position which is neutral to the underlying, sort of a delta type hedge, and neutral to the exposure to these factors. And because this is something that's sort of inherently static, because we just eliminate the dependence of these factors, this is independent of our Neural-SDE dynamics. So this is purely a feature of the factor representation, that we want to make the position neutral with respect to these factors. And because we have a linear factor representation, it's as simple as solving a linear system to make the portfolio factor neutral by a suitable choice of the position in the underlying and a number of other hedging options. So to bring the dynamics into play, I'm also going to look at minimum variance hedging. So we're considering these portfolios over a single period of time. Our dynamic model tells us about the joint dependence of all these factors. And then what we do is we make sure that the projection of the replicating portfolio onto all of these factors is zero. So we want to eliminate the dependence so as to minimize the variance of our hedged position. Okay, so two approaches: sensitivity-based, independent of the dynamics; mean variance-based, of course, dependent on the dynamics. So we're testing this on a huge set of options, positions that we are going to hedge. So that ranges from a naive portfolio, which is an equally weighted portfolio of a whole range of options, two outright options, so they would be single options for a certain strike and maturity. So there's 70 of them to various delta hedged or not hedged positions. So a huge set of different portfolios that we're hedging either by factor hedging or by simple delta hedging. And then we're measuring some sort of quadratic hedging error. So sort of the variance of our hedged position, either sort of statically or an exponentially weighted moving average. So what I'm showing you on the next slide is exponentially weighted moving averages of the quadratic hedging error. So on the left here, I'm showing you the daily rebalancing case, and on the right, I'm showing you the weekly rebalancing case. So maybe starting on the left, so this is now plotted, this exponentially weighted hedging error from beginning of 2020 to roughly the end of 2021. And we see that sort of at the beginning, the hedges worked quite well, but then that was the beginning when COVID hit. So then we enter the dynamics, which was unseen in our training period. So suddenly the hedging performance jumped up and became a lot worse. So in the case that we're only hedging with the underlying, all of the hedges have a massive hedging error of up to 20–30%. So that's true for the Black-Scholes delta hedging. So that's the blue curve. That's true for the Heston mean variance hedging, and that's also true for our Neural-SDE model mean variance hedging. On the right-hand side here, I'm showing you the similar picture for weekly rebalancing, and the hedging performance is even a lot worse. So now, if we, on the next slide, I'm going to introduce extra hedging instruments to hedge an additional factor. So we will now hedge with an underlying and an additional option to neutralize the sensitivity with respect to S and with respect to basically the volatility factor. So I'm showing you now 4 different hedges. The blue one is sort of the benchmark. That's a Black-Scholes delta Vega hedge, and anybody who's sort of Black-Scholes delta Vega hedged before in a sort of model-based way finds that they're actually quite hard to beat. So the hedging error here is sort of in the range of 4 to 6% for the Black-Scholes delta Vega hedge. I'm also showing you the hedge that is based on the Heston model. So at every time you calibrate the Heston model, you back out your hedge ratios from the Heston model and you hedge your market like that. So that's the sort of the orange curve here. And then we perform both the sensitivity-based and the mean variance-based hedge under our model. And it turns out that in this case, the mean variance-based hedge is the one that has the best hedging performance. Interestingly, if we go from daily to weekly rebalancing, it turns out that the order changes slightly, and in that case, it's actually that the sensitivity-based hedge performs slightly better. And so our interpretation for this is that the mean variance-based hedge is exposed to forecasting the dependence of the returns of the factors. And that's something that got severely disrupted when COVID hit. So it is not well trained, and therefore it performs not so good over longer rebalancing periods. We repeated the exercise over different periods, for instance, not over the last 2 years, but over a more benign period where the model is well trained, and we found that more consistently the mean variance-based hedge performed the best. So we have a lot of these tests in the hedging paper. So in my last 5 minutes, in my last 5 minutes, I want to now show you how you can use the learned model also for value at risk simulation. And we picked value at risk because it's common and easy to compute. But given that we have at our disposal the whole dynamics, we can generate profiles to compute other risk measures that have better properties like expected shortfall or other favored risk measures. So what we do is so we train our market model, and then we check the residuals. So for every given point in time, we put in the values into our model. If this was a true discretization of an SDE, you would expect Gaussian increments. But what I'm showing you here is scatter plots of the true residuals that come out of our model. And we see, of course, that there are more fat tails. So that is true on the right-hand side, where we have the residuals for the underlying, and that's even more pronounced for the factors Xi1 and Xi2. I'm also showing you the residuals sort of as a scatter plot for pairs of components. And what's reassuring here is that the residuals, they seem sort of independent, right? So you get a roughly sort of circular shape here. But given that we have this non-normality, what we do is now that to actually simulate our SDE model, we train the model, but then instead of simulating Gaussian returns in an Euler scheme, we replace them by historical returns. So we compute the residuals from our 10-year historical time series on a, say, daily or weekly basis. We take all of these triplets of residuals, we put them in a big hat, shake the hat, and every day we pick a triplet of residuals that we then plug into the simulation for the forward simulation. Put it back with return and pick the next residual. Okay, so we use the historical returns for the risk simulation, but based on our discretized Neural-SDE model. And so this is my last results, where we then test this approach of risk simulation against filtered historical simulation, which is something that is quite popularly used in central banks and regulators. So filtered historical simulation in the sense that we every day fit a Heston model, and then we estimate a dynamical model for the Heston parameters, and then we use that to forecast the time series of option prices, filtered historical simulation. And we can test this on a wide array of different portfolios. So we do this for outright options, 140 of them, with certain delta exposed positions, but also delta hedged positions like butterflies, delta hedged options, calendar spreads, and so on and so on. So there's hundreds of different positions that we did this risk simulation for. And in this table now, I'm showing you the performance of the Neural-SDE model compared to the filtered historical simulation. So the first line is the coverage ratio. So this is simply to say that if you compute 99% value at risk and you simulate forward, you would hope that in 1% of the cases you breach it, and in 99% you do not. So this is what we mean by coverage. And so given we perform this for a huge range of portfolios, we compute this coverage that we hope to be 0.99. We compute it for all these portfolios, and then we compute the median and the mean. And we see that the median is quite close by 99% for both the Neural-SDE model and the filtered historical simulation, whereas the mean we are quite close, but the filtered historical simulation is a bit too low. So the interpretation being that there's a few cases where it significantly underestimates the risk. There's a couple of other common tests. So one is the cubic probability of failure test, which is simply a hypothesis test where the null hypothesis is that the breaching the value at risk or in each time interval is an independent Bernoulli trial with a null hypothesis of p-value of 99% against the general alternative. And we see that in 7% of our portfolio, this test fails, whereas for filtered historical simulation, it fails in 25% of the cases. So a significant rejection rate. There's the Christoph independence test, which essentially tests the null hypothesis that VAR breaches on consecutive days are independent. So in our case, we fail this in less than 1% of the cases, whereas filtered historical simulation fails more than 10% of the cases. And finally, there's a sort of very crude measure as the Basel traffic light system, which essentially looks at 250 consecutive days as a test period. If you compute the 99% VAR over this period, you expect to breach it 2 or 3 days out of 250 days. So you get a green light if you don't breach more than 4 times. You get a yellow light if you don't breach more than 8 or 9 times, and otherwise you get a red light. And we see that we managed to avoid a red light in almost all the cases whereas the filtered historical simulation gets a red light in 10% of the cases. So it seems to be that our model is superior against this one benchmark. And a further advantage is that it is extremely fast to compute, because once it is trained, the forward simulation has a negligible computational cost, whereas for something like filtered historical simulation, you would have to compute Heston prices every time for your whole universe of the options that you are considering. So the computational time is significantly faster. Okay, so I think this is good timing. So I want to wrap up and just offer you some conclusions, namely that what we find a particularly powerful combination is the one between machine learning methods, but feeding in fundamental economic modeling into our prices, which facilitate the training process, but more importantly, make sure that the prices we predict are actually financially meaningful. So we saw that this has hedging performance, which is on par with standard volatility hedges that are currently being used, and outperforms traditional approaches of risk simulation at a much lower computational cost. So we're currently working on extensions of this. So what I showed you was for European option books. We also looked at volatility indices, which we have partly included in the paper. But it would be interesting to look at a more diverse range of options, including American and exotic options. But the main difficulty there is that you don't have such a straightforward characterizations of the absence of model-free arbitrage, which would be something very interesting to think about there. But in principle, the whole paradigm should still be applicable. Okay, I'd like to end here, and so I'm looking forward to a discussion.
Thank you very much, Christoph, for a very interesting and nice talk. Now we move to the part where we open the floor for the questions from the audience. And again, you can type them, or just if you can unmute yourself, or raise your hand and I'll unmute you and you can ask the questions. So if there are any, perhaps I'll start with one question, and then we'll have more. So in the last minute, actually, I wanted to interrupt in the middle to ask, but then you mentioned about the time to perform the simulations right in the middle, the last slides. So in order of magnitude, so in the first part and the second part, how fast actually is the training itself? And then, of course, once you train, it's fast, but the training of the algorithm.
Yeah, I would say that it's sort of in the range of minutes. So yeah, that's an interesting question. That's also where we found that because of the restrictions that we have, the training time is a bit larger. The convergence is a bit slower than if you have no constraints on your model. But you start off with a better guess. So in some sense, so the convergence is sort of flatter, but because you start with something that's already restricted to something meaningful, the initial error is a lot smaller. But then, so in the papers we plotted a lot of the loss convergence curves, and you sort of get the typical picture, the fairly steep decline, and then it sort of levels off. So it depends a bit on your network architecture, of course. So we found that there's no value in having the neural networks too rich. So some optimum being in most of our cases of around something like 2 or 3 hidden layers, something in the range of 250 or so nodes per layer was something that already was rich enough and had a sensible training performance.
I see. So, yeah. And you even answered the question that I wanted to know about the design of the neural network, but you already said that too. So, so yeah, thank you, thanks a lot. So, Christoph, any other questions from the audience?
Yes. So thank you very much for this talk. My question is so in this in this slide, you say that the extension for exotic options is on the way. So for an agent in the usual setting of neutral pricing, we usually go the route of increasing the dimensionality of the state space, right? Is it possible to do something similar here, at least for an agent?
Mm-hmm. Yeah, that's okay. So that's a good question. Yeah, so one step you have to think about is what you choose for your factors. One could consider, in addition to having the spot price, also to introduce the average as a sort of derived factor. And as you said, if you were to price to make the model Markovian, so that could be one thing to learn the dynamics for the average as well, and then somehow ensuring that the consistency with the model. I haven't thought about what would be the sort of model-free arbitrage conditions for an option like an Asian option that you want to satisfy to constrain your joint state space. So that is maybe the most model-specific step that you would think about that you have here. So apart from that, I mean, then the training of the SDs, etc. I mean, that is generic, and we just use standard tools of doing this. So I think it would be a matter of mostly just thinking carefully about constraints on the prices of your exotics, for example, Asians in the state space. So that's something that I think takes more time to think through than I can take now. Yeah.
Thank you very much.
Yeah, you're welcome.
Okay, so we have a question in the Q&A chat. Does the framework address the dynamic arbitrage as well?
Yes. So this is something that we have thought about, but sort of parked a little bit. Sort of just our motivation was to focus on the static arbitrage case because of it being model free, whereas for dynamic arbitrage, for anybody to actually exploit it, you'd have to know the precise model that we are using for the simulation, whereas static arbitrage is simply evident from the prices. So that's why we thought that static arbitrage is the first one to focus on. So you're already introducing potentially dynamic arbitrage by the reduction to the factors. So you go from an option surface where we start with potentially hundreds of prices, and then we're reducing it to two factors, right? So to ensure that you have no dynamic arbitrage, you would want to have a risk neutral measure which turns the processes simultaneously into martingales, so which is equivalent to the existence of a market price of risk. So we derived conditions for the existence of this market price of risk, and as you would expect, because you go from hundreds of factors to two factors, you have a massively overdetermined system that you have to satisfy for your market price of risk process. So essentially, you have something that has a very bad rank. But what you see is that depending on how you choose these factors, you might be closer to the span of your matrix, of your system matrix. And that was in fact one way how we included factors into our model, to choose factors which sort of we projected onto the column space of our linear system to sort of minimize, in some sense, the arbitrage that we're introducing. But that is something that, from a theoretical perspective, would be interesting to make sure that we can reduce the dynamic arbitrage in our model itself. So yeah, that would be sort of the place to start to think about that. Yeah.